Good morning. Can you hear me?
Good morning,
Can
sir.
just yeah,
Yes,
thank
sir.
you.
Good morning.
Can you see the shared screen?
Yes, sir.
But why I am not able to see that? So you are able to see the Jupyter notebook?
Yes, sir.
Okay. 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 So today what we will do is we will try to do the fourth practical, and this is basically practical to apply various different types of image enhancement, specifically using the derivative filters. Okay, we have already discussed in theory that how does the differentials help you to perform various different image enhancement. Specifically, we have discussed about the first order derivative and the second order derivative. So if you look at the first order derivative, examples we have seen, the Sobel, Privet, and Canny, and many other different types of spatial mask. And then second order derivative में आपके पास Laplacian था and so on. So what was one observation that we have seen, that when you were calculating the gradient along x and y direction respectively, you were able to detect the edges. Okay, and when you detect these edges could be basically able to help you to characterize the images, and therefore much of the information about the image can be basically being obtained. So whenever you have any kind of a problem, it will be required to basically specially process and identify such informations from the image, and we go for the spatial processing for that. And in theory, we have also seen that how to develop basically spatial mask using this first order derivative and the second order derivative, and further how this can be basically used for other similar kind of problems. So we basically now take up the problem of writing a program for various different types of image enhancements. Okay, so various different types of image enhancements done by the image derivatives. Okay, so we will be calculating the image derivatives, and specifically इसमें दो चीज हम देखेंगे, जिसमें है आपका implementing the gradient and दूसरा है Laplacian. So this is basically the first order, and this is going to be the second order part that we are going to use. So Let us now um, include our um, packages or the libraries which we'll be using. So largely we have already identified those set of packages and the libraries that we will need. Okay, so the same is going to be basically used again here. So I will be using import numpy. Numpy is going to be used, okay, in most of the cases. Import numpy as NP. Okay, so NP is my alias that you are going to have. Then we will use SciPy package, and from there we will use the signal, and we'll use miscellaneous. We will use ND image. Okay, so we are just importing all of them together, and then we'll start utilizing them. Okay, import signal, miscellaneous, and ND image. Okay, now depending upon kind of operation that you want to do, you will be basically using any of this. SciPy, SCI, SciPy. Then you will also use SK image. So I say from SK image. Okay, I say import. We will be using various different types of filters. So I can say that filters. Okay, and we will also use features. Okay, and you have img as float. Okay, because most of the time जब आप कॉल कर रहे हैं तो in that case you may be using the float dn values. Then you can also use the IO package. So therefore, from sk image dot io, I say import I am read. Okay, so if you want to read the image, I can just use the IO package. There are various different libraries and packages which you can use for reading the image. Okay, so you can use PIL. You have got SK image. You have others also. So with this time we will be using IM read for that. And then we have from sk image dot color. I say import RGB to gray. Okay, so you have RGB to gray. So why we are using it? Because we want to basically convert our multi-channel image into a grayscale image, and for that this is being used. And then I'm not sure that still कि PIL हमारा चलेगा या नहीं. I have not yet resolved yesterday's problem, but we'll still try. Okay, so we have import PIL. Okay, from import I will say image and image filters. ठीक है, image filter हम use करेंगे, and then matplotlib is by default going to be there. So import matplotlib dot pylab as pylab. ठीक है, ये हमारा alias हो गया. So I hope कि all packages are there. So let's try. After that, once all these things are being done, we will try to implement the gradient and the Laplace. So somebody please once again give me a go that I am audible.
Yes, you are.
Thank you. So now let's implement derivatives and gradients. So for this, we'll write our old function that is plot images. Okay, you don't need to do this, but still एक convention हमने बना लिया है, तो we will just use so that we can just pass the image and the title, and I will be able to. Okay, so we have. So basically, we will be writing our own what is a function for plotting the image with the titles. Okay, so we had pylab dot im show, and we'll pass our image that is to be shown, and then I say pylab dot title. Okay, and title हम pass करेंगे title, and you have a size, and I say size equal to say 20, whatever size you want to have, you can just have that. and then we will also say pylab axis off कर देते हैं, pylab dot axis off. Okay, if you don't want to do this, that's fine. Okay, basically we don't want to show the axis, okay, for our plotted figures. For that we are doing. Now this is being done, so let's say, yeah, so we will be calling this plot images for plotting our image. So now let us try to define our kernel. Okay, so we will be trying to define our kernel, say kernel X. Okay, so I want to calculate the gradients along X direction and Y direction. So for that, if you remember in the class, we have discussed various different kind of kernels. We wanted to find out the change along the X direction and the Y direction respectively. So I can just create my kernel manually. Okay, and let me say that this is -1 and say 1. Okay, and we will create kernel Y. Okay, so I say kernel underscore Y is equal to, I say -1. Okay, so along the y direction, so 1. ये हमारा मैनुअली हमने कर्नल बना लिया है, so that is magnitude आपने उसमें specify किया. Now we will read our original image. Let me say I am equal to, I am going to use I am read for the image. Okay, so I say I am read, and all my images are under the images folder underscore let's say use the same image that we have used, rkm.jpg. Okay, now see that this is basically a multicolor or multi-channel image. So since we are most of the image processing, okay, routines are better applied on to RGB, what's a grayscale images. So what we will do is that we will try to convert our images into RGB, and for that we have imported our package, if you remember, skimage.color. So what I'll do is that I will convert it to RGB to gray. Okay, I have just converted my multi-channel image into a grayscale image. So my IM object is containing the grayscale version of the image, and that's the RKM. That's this image that we have applied it yesterday also. So now let's try to apply this kernel and calculate the gradient along the X direction and Y direction, and try to see that what do you basically get. So I say that IM underscore X, the image, okay, the gradient you are going to calculate, or the transformation calculating along the X direction. So I want to find out the changes that are happening along the X direction. So remember when we have studied about our partial differentials, we just said that partial differential along X and partial differential along Y, and that gave you the rate of change of the color or the shades that you had. Okay, so that's what we are trying to implement, and for this I will be basically making use of the signal package, and from that we are going to have a convolution, a two-dimensional convolution. The reason is very obvious that you want to have a two-dimensional convolution because image is basically a two-dimensional, okay, arrangement of intensity in a grid format. Okay, so one along X and one along Y. So for that I just say signal dot convolve, okay, 2D. Okay, so you can have one-dimensional convolution also and two-dimensional convolution. Since it is an image, so two-dimensional है, so I'll just say original image को हम convolution करेंगे, and in convolution with what? Basically, we are going to apply a filter or the kernel, and हमने हमारा kernel already बना के रखा हुआ है. If you see for along X direction, you have kernel X, and then for Y you are going to have kernel Y. So I just apply kernel underscore X. Okay, so sorry. So I just said that I need to have kernel underscore X. Okay, so IM is my original image and kernel X is my filter, if you see. Okay, so that is for the X direction. And then I say mode, we are going to say, let's keep it default. I say same. Just a second. Yeah, so coming back to our problem, so we just have applied our kernel that we have created, and let's apply it along the y directions also. So अगर आप y direction में कहें तो we can just copy this, and I can just paste, and this time it is going to be along y. So signal dot convert to the image kernel, and this time I will apply y kernel. ठीक है? Now, once you have applied your kernel or the mask onto the filter, obviously you'll find that there are some changes that will be obtained, and that is basically calculating the gradient change along the x direction and the y direction. Okay, so that mask that we have created, that is corresponding to the gradients. Now, when you have calculated its differential, so you'll see that there are two aspects that you may be interested in looking at it. One is the magnitude of that gradient, and then you have a digression or use direction. Okay, so let's try to calculate the magnitude of our image, that is a transformed image. So I say that in image magnitude, okay, is equal to, and for this what we will do is that I will say np. Okay, we will use numpy. I say numpy dot sqrt. Okay, if you remember, square magnitude was nothing but the under root of that x square plus y square. Okay, so I'll just calculate my uh, im underscore x. Okay, so after the gradient along x, im x है, and we'll say power to 2. Okay, so x square, and I will say im underscore y raised to 2. ये हो गया आपका magnitude you have calculated. Okay, so we are just calculating it, and later on we'll also try to visualize it, and you will be seeing that this is effectively trying to have a very uh, interesting result. Okay, you'll see that some kind of an embossing effect or something similar to that can be obtained with this gradient changes along x and y direction respectively. Let's talk about image direction. Okay, or जो direction है. So direction के लिए you will see that you will be basically calculating the tan inverse of say change along y divided by change along x. So I'll just say that np dot arctan. Okay, and I say im underscore y divided by im underscore x. Okay, so that's what you see that the changes along y divided by changing along x. So you will get magnitude and the direction. Now let's go ahead and now try to start plotting it. I say pylab dot gray. Okay, and then we'll pylab dot figure. Okay, and whatever size you want to have, you can just specify. Let me just make it say 3020 here. In this case, you can have 1020 or whatever it is. Okay, so if you are going to have bigger, just so the bigger images are going to be formed. That depends upon that what you want to basically show and how much is size. Now let's plot this, and this time I will be plotting multiple images. So let me say pylab dot subplot say 2 3 1. Okay, so 2 cross 3 and 2 cross 3 का जो आपका पहला image है, that we are going to plot, and I say we'll call our custom function. So I say plot underscore image, and I will plot my original image. Original image हमारा क्या था? IM था. And then I say give the caption. I'm saying original. Okay, this is the original image. ये हो गया आपका this, and then we will say second करते हैं. I say pylab dot subplot, and I will say 232. Okay, so second image आप plot कर रहे हैं, and this time what I'll do, I'll say plot underscore image, and this time I will plot the gradient of the image and gradient of the image along x direction. Okay, so I'll just try to see that what is the gradient change or the color changes along the x direction. और उसके लिए हमारा image था im underscore x. We have applied the x kernel there, and then you will just say caption within it. Let me say this is gradient x. ये हो गया आपका original and gradient x, and similarly you need to also give the gradient y. So let me just copy this as it is. Okay, and this time it is going to be 2 cross 3 the third one, and this is going to be gradient y, and let me say this is gradient y. So original gradient x and gradient y has been plotted. Okay, so now you may also be interested in say plotting the magnitude of the computations that you had. So now let's just try to see that how does that look. Okay, let me say pylab subplot, and let's say fourth one, and this time this is we have already calculated magnitude. Yes, I have calculated magnitude. Let me say magnitude, and magnitude को हम लिखेंगे like this. Okay, so we'll say double pride, and I say gradient. ठीक है, ये हो गया आपका gradient that you are going to have. And then fourth thing we have already plotted. Now let's say pylab dot subplot 235. That is the fifth image of the 2 cross 3 grid. And this time we will be plotting the directions. Let me say image direction, DIR. Okay, in the previous practical also, if you remember when we applied the processing in the frequency domain, we have seen that when we have calculated the fast Fourier and inverse fast Fourier, at that point in time we have plotted the gradient also and the direction also. Okay, so for both the images, if you recall, we had an elephant image on the grassland, and then we had one image was that Olympic wala image. So in both of the cases, you have seen that how the direction looks like in both of the cases. Um, yeah, so we will just say that image direction, and direction हम plot करते हैं यहाँ पे. Let's say, let's give the caption also for that, and let's say R, and I say dollar theta. Okay, THETA. Okay, so we are going to say that theta. ये हो गया आपका. Yes. We have plotted the theta, and then let's go for the next plot, that is 2 3 6 sixth image we are going to plot. So this time we will be trying to plot other things. Okay, so this time I'll just trying to see the range. So I say range, and I will say IM dot shape. Okay, if you remember the shape 0 and 1, that is going to give you the dimensions. So let me say shape 1. Okay, फिर उसके बाद I'll say IM and 0th row and all columns. And then other things also we can just put that. So let me just plot that. So I have already run this. So let's say this. Okay, so we have just run this and see that if we get some suitable results. Kernel Y is not defined. Okay, so kernel the spelling mistake. It is kernel Y. Now what is the error? Okay, fig, unexpected argument fig. Okay, where pylab dot figure, pylab dot figure. Yeah, fixed size. It should be fixed size. Should be fixed size. Now what is the error? Plot image. Plot image is not defined. Plot image is not defined. Okay, so did I run that? Acha, we have said that it is plot images. So whatever function you are writing, the same function has to be used. Now this time name size is not defined. Okay, pylab dot size. Okay, so we have written it twice. Okay, so this is pylab image title. Size, yes. Okay, so we just had written it twice. So let me just try out. Yeah, now you just see that this is a very interesting thing. So original image, okay, we converted it into a grayscale image, right? And you can see that the second figure and the third figure that we have plotted the gradient x and gradient y. Now you must understand that when you are calculating the gradient, gradient is basically calculating the rate of change along the particular direction, and one was the x and another was y. Now, if you look at the figure, original figure was basically a portrait, okay, wherein you have the shirt, and your shirt has got stripes. Now, when you're calculating the gradient along the x direction, you are basically trying to find out the changes, and you can see that the vertical stripes are more visible in this case, while in the second case, when you have gradient y, you'll see that the horizontal stripes are comparatively better visible than the vertical. Again, that depends upon that what is how much is it is vertical or it is inclined. You can also see that other things, okay, specifically just see, because when you are looking at the eyebrows के जो आपके hairs हैं, that is running from horizontal left to right, and therefore the not much of the change in the gradient x. When you see the gradient y, okay, you will be able to see the changes. Even at the hair at the top, you will see that, okay, the second figure is able to what I say extract more changes, and you can see even the stranded version of the hair also. So ultimately, you will see that this is basically telling you that how much amount of gradient change or the color changes are happening. And in a sense, you'll see that what I have done is that I have tried to see that whether there is exists an edge. Okay, so we are basically trying to find out whether the pixel lies onto the edge and all. Now, if you extend it further, if you are going to take it for the second order partial differential, if you are going to calculate along the two, uh, then so you will be able to basically detect the edges, and you may be also able to classify that whether you happen to be lie onto the left side of the edge or the right side of the edge, and so on. For edge detection, particularly, we will be using the second order, that is the Laplace transform. Okay, for most of the cases. Okay, so let's now just try to understand. Okay, and implement it further. So ये है आपका result. Okay, so we have plotted the gradient x and gradient y, and if you see that the magnitude of the gradient when I'm trying to plot, that is under root of say gradient x square plus y square. So that is what you can see, and that is in a sense telling you the edges that are there in the image, and you can clearly see that eyes, okay, and the hair boundaries and the vertical stripes are more visible in this case. And when you look at the third figure, so third figure is basically trying to give you the direction changes. Now, one very important observation you can find out from the output, okay, and you can just recall the output that we have seen in our previous practical. Okay, if you remember the whether it was an elephant case or whether it was that portrait of Aditya, in both the cases you find out you had a background, and the background had a gradient change, and therefore the direction for the background was also being formed. Now in this case, this portrait image, okay, this is my image, and this is basically taken on relatively green screen. Okay, so when you have a green screen and there was not much of the gradient change that is happening, altogether in the background it was green. So therefore, you have a relatively a flatter background, and there was no change. And therefore, you see that in the output also, you do not get the gradient directional change. And that's why you just see that most of the things are white. White for the other region, that is the portrait of the image, you will see that specifically in the face region. So when you look at the face you'll find out depending upon the light vector, you see that the directions, okay, and changes and the gradient is more visible. You will be able to see some kind of a 3D depth kind of a thing. So in the face region there is a lot of changes into the theta or the direction, and in the what is the short region, you'll see that there are still changes, but that is not in the same. So basically, what happens is that this will be able to give you some kind of information about the composition of the image and possibly directional things. In fact, I can extend it to further high dimensional space, and we may be able to approximate it further, generating the 3D surface for the given this two-dimensional image also. So that's why you just say that this differentials what you have studied in your 11th, 12th, and so on. Okay, they have got a great application in image processing. Okay, so we just plotted it for our case, and we have just seen that the gradient along x and gradient along y direction. Okay, so that was one practical we just completed. Now let us try to see something um, different. Okay, now let me say. mm, you can try out with other image also. You, in case of other image, you will see that there will be possibly a different output based on the composition of the image, because that depends upon that how fast and how closely the shades of the color are changing. Okay, so if you have a image which is very fine and very smooth changes are happening, so in that case edges may not be visible and the directional changes may not be as sharp as what you achieve in this case. Now let us see the second one. This time I will be calculating the Laplacian. Okay, let's say Laplacian. Now, what is Laplacian? If you see that Laplacian is nothing but the second order derivative. Okay, so let me say Laplacian filter. This is the second order derivative filter. If you remember the f by um, double square f by double x square double y square. Okay, individually along the say x direction and the y direction, you wanted to calculate the second order partial differential. Okay, so and we have also generated the spatial filter for the same. Okay, we have seen that the functional and mathematical definition for that, and we have identified the coefficient, and finally we generated our spatial mask for the same. And assuming that that spatial mask is being already obtained, what we can do is that either we can create our own mask with the relevant coefficient, or we can use the existing libraries and उसमें से आप Laplacian directly use कर सकते हैं. So let us just try to create our Laplacian mask ourselves. So I am saying that I'm going to have let's say sorry, इसको हम let's say Laplacian. I say kernel. Okay, so Laplacian kernel or the filter, we will say kernel Laplacian. Okay, so Laplacian. Okay, this is my variable. I say I'll be creating as nested lists, okay, which will be basically, or I can say that we'll create a matrix rather than. So let's say first row is 0, minus 1, 0. If you remember the Laplacian, top row was basically 0, minus 1 and 0. Second row was minus 1, 4, minus 1, and third row was basically 0, minus 1, 0. So accordingly, you can just see that if you try to see in terms of four neighborhoods, top, down, left, and right, वो आपके negative values थे, and central component was basically positive. And that positive value 4, it came because we had the contribution from the horizontal and the vertical directions. Okay, so 2 and 2 were there, and that amounted to make it 4. So let's say that the second row I am saying minus 1, 4, and minus 1, and I say third row is 0, minus 1, and 0. Okay, right? So in our theoretical class, we have seen that how this filter was been designed. Now remember, whenever you are applying any kind of filter, it is very important that order of the filter or the dimension of the filter must be looked into. So if you want to have a point pixel processing, so usually it is ideal that you need to have a 3 cross 3 filter. Okay, and all the filters or the mask, they need to be generally the odd order. There's no hard requirement, but if you are going to have an odd order filter, then that way the symmetry can be basically maintained, and we will be basically using the 3 cross 3 filter here in this case. So now let's just try to load our image. Let's say image equal to this time again we'll convert it into grayscale. So I say RGB to gray. Okay, I have got I am read, and let me say images folder में से मेरा image था say we are going to convert. You can take any images. Let me take this time and another image. We have got a folder called as a image. In that case, I am having CGVR. This is basically a cover page of the book. Okay, and I said PNG. This is a PNG file. You can just change any other image also. Now I will calculate my transformed image. Let me say image 1 equal to, and I will apply this kernel on my image. Okay, so I will use the two-dimensional convolution for that. Let me just use numpy for this, np dot clip, and I say signal dot convolve 2D. ठीक है, सिग्नल डॉट कन्वॉल्व टू डी किस पे आप कन्वोल्यूशन कर रहे हैं, ओरिजिनल इमेज राइम पे कर रहे हैं, किससे कर रहे हैं, आपका कर्नल क्या है, कर्नल ऐसे कर्नल अंडरस्कोर लैप्लाशियन. Okay, remember Laplacian kernel we ourselves have created. Okay, manually हमने create किया, इसको coefficient हमने दिया हुआ है. Okay, and let me say mode equal to sim, right? And then we'll just leave other parameters as default. Okay, and then we say pylab dot gray. Okay, pylab dot gray, and then we just start plotting our output. हम original plot करेंगे and we will plot the convolved image. Okay, convolution किससे किया है आपने? You have done it with the Laplacian. So in that case, I am expecting that in the output I will be getting the edges, because if you remember second order partial differential, it was basically helping you to find out the edges from that. So Laplacian was having an equivalent effect of detecting the edges from the given image. Okay, so given image in this case, this is there. So let me say pylab dot figure, I say fig size, okay, equal to जो आपको यहाँ पे size चाहिए वो ले लीजिए. Okay, the image is very big, then that you can scale it down using fixed size. So I say that. ठीक है, मैंने 2010 कर दिया. Let me say pylab dot subplot. Okay, you can plot it individually also, but generally I follow this approach. So you can just plot it in form of a grid. So I'm saying, let me say plotting a 1 cross 2. Okay, so 1 row, 2 columns. Okay, so I'm saying 1 cross 2 and उसमें का first image. Okay, there are two ways of specifying things. 1 to 1 आप लिख सकते थे या 1, 2, 1 भी लिख सकते, दोनों एक ही काम करता है. Okay, so 1 to 1, that is the first image that I want to plot it, and I will use my function plot image. Okay, and we want to plot an original image, so I am, and then I will give the caption original. ये हो गया आपका पहला image आपके 1 cross 2 image का, and this is the original. And now I want to plot the second image, which is basically a Laplace transformed image. Okay, so I say pylab dot subplot, and I say 1 cross 2 ka second image. So 1, 2, 2, and I say plot underscore image. Okay, and I will pass my transformed image. This is nothing but the transform image. Laplacian transformation आपने किया है, and I'm expecting it to show the edges. Okay, so now let me give the title. I'm saying Laplacian convolved image. ठीक है, जिसमें हम कहेंगे कि हम एक्सपेक्ट कर रहे हैं कि आउटपुट जो होगा convolved, okay, image. And let me say pylab dot show. ये हो गया आपका. So if everything is right, then you should get some interesting results. Okay, so obviously there is an error. The input array must be having size 3 along channel axis, got 201, 15, 6, and 4. So image is having problem. I'm RGB to gray. I am read. Let's see what happened. Sometimes image is it. Let me say इसके पहले क्या यूज किया हमने, कोई PNG image दूसरा देखना पड़ेगा. So POARO.png. Still there is a problem. RGB equal to prepare color space RGB. Okay, coefficient मिला 0.217172. Okay, have input array must have size 3 along channel axis. Okay, so we did not get that. तो let's say हम PNG की जगह हम करते हैं दूसरा इमेज ले लेते हैं. लेट मी से RKM JPG ट्राई करके देखते हैं. RKM JPG. ओके, कर्नल लैप्लाशियन इज नॉट डिफाइंड. स्पेलिंग क्या गलत लिखा हमने? कन्वॉल लैप्लाशियन. ओके, लैप्लाशियन स्पेलिंग क्या है? लैप्लाशियन. अच्छा, हाँ, केस सेंसिटिव है ये. So again, plot image is wrong. Plot image which line? 122 का plot की spelling. Okay, now look at it. See this. Okay, so you have the same image we have just taken. Now again, remember whenever you are applying, that depends upon कि आपका image का format क्या है. Depending upon that, a suitable package or a function has to be used. Okay, so this particular RGB to gray and IM read basically works on JPG image properly. PNG के लिए you can use the PIL or Pillow library. उससे आप कर सकते हैं. So now you see that observation of this. I am able to detect the edges, and you can see the edges in the vertical direction as well as the horizontal direction. Specifically आप edges अगर आप देखें तो आपको ये stripes of the shirt जो है वो बहुत अच्छे से दिखाई दे रही है, because that is a true edge in our case. Okay, the vertical as well as the horizontal or any other that you can see, or even at the background, if you see that the boundaries of the hairs, okay, when suddenly the black hairs are changing into the background gray, which is basically effectively the green screen. So whenever there is a sharp change in the intensity, okay, we define it as an edge. And the second order partial differential, that is the Laplace, is basically intended to finding out that sharp changes into the intensity, such that we will be able to classify some pixels to lying to the left of that edge or the right of the edge. And that's why you said that the hair की जो boundary है आपको, ओके, जो कैप है वो क्लियरली दिखाई दे रहा है. इवन एट द ईयर lobes you'll see that ear has got some design. Okay, you have some dips and you have some crescent trough kind of a thing. So in that case, wherever it is brighter, okay, that is assumed to be the high and the dips are the lows. So gradient वहाँ पे आपको बता रहा है कि कहाँ पे low है and high, so that edges are being found out. Even in the eyes you can just see that, okay, and near the mustache and so on. While in the areas of the forehead or at the cheeks or the chin, you'll see that there is no change. Okay, so not much change, so therefore there is no edge near that. Okay, and other edges are quite visible in the case of the shirt and so on. So if I just have any other image, let me just try out with something else. Okay, any other image, let me say checkboard.jpg. I say checkboard नहीं, board.png हो गया. Elephant, let's say Elephant, elephant 2. So again इसमें नहीं होगा, नो सच फाइल. एलिफेंट नहीं है इसमें. एलिफेंट, ELEPHANT, एलिफेंट. Laplacian of the image, that is the first order and the second order derivative. So these were the filters that we have applied. And now let us try to um, apply some more things. One more thing that you can see is that Laplacian, if you see that you have detected an edge. Now, if you add this edge component in the original image, you will find out this will have an effect of sharpening the image. Okay, if you remember when we have talked about the high pass filters and this thing, we have discussed about high boost filtering, and we have talked about the unsharp masking and so on, where we have added some component of the original image in order to highlight it further. So what I can do is that I can actually combine this Laplacian with the original image, and my original image may be much crisper without the loss of any of the say lower frequencies or the lower gray shades. Okay, let's see that what happens if I'm going to do that. Let me say sharpening. Okay, so I'm doing sharpening with Laplacian. Laplacian. Okay, so sharpening के लिए आप normal high pass filter लगा सकते हैं. But let's see that what happens with this Laplacian. So let me say from SK image dot filters. In fact, we have already imported it. Okay, import Laplace. There is a inbuilt function called as an Laplace. हमने यहाँ पे क्या किया? We have created our own Laplacian function. Now we are going to import the Laplacian function from the SK image. Okay, and let's now say I am equal to RGB to gray, and I'll say I am read, and from my images folder I'm saying there is a file called as a board, BOARD, board.png. Okay, board.png is there. Okay, so it is images. Okay, board.png, and we will just try to use this, and I will calculate my transform image, that is im1 equal to np.clip, and I want to apply the Laplace. Okay, Laplace of what? Original image. Now this will calculate the Laplace of the original image, and you can just plot it, and आप देख सकते हैं कि आपको क्या आया है. But now I'm saying that I want to use it for sharpening of the image. Sharpening के लिए हम क्या कर सकते हैं कि Laplace जो आपने calculate किया है, जो edges मिला है, that you can combine with the original image. How do you combine it? You just add the original image to this Laplace, okay, and keep the other parameters as it is. ये हो गया आपका sharpened image. In fact, let us just try to see that whether it has really improved or not. Okay, so इसके लिए let's just say pylab dot figure. Okay, and let me say fig size equal to, हम छोटा ही करते हैं, so 1015 हमने डाल दिया. ठीक है, and इसके बाद हम सब प्लॉट करेंगे. we'll just try to plot 1x2. so I say pylab dot subplot, and let's say